So this is lecture 9. We're going to talk about system transfer function and the Laplace transform. So it's the 9th lecture out of a total of 11 lectures. So we have 2 more lectures to go. So last week we spoke about the impulse response. This week we're going to talk about transfer function and Laplace transform. And these 2 lectures are closely linked. And the next 2 lectures are closely linked, just like lectures 4 and 5 were closely linked. So we are literally almost there. We have 2 lectures to go, and that's the end of this 15-credit module. So as a reminder, last week we spent a lot of time introducing this idea of an impulse response. And we said the definition of an impulse response is the output of a system when the input is a unit impulse. And a lot of what we spoke about last time was about linear time invariant systems. And we said that when the input is an impulse, the output is the impulse response. If the input is a step, the output is a step response, and if the input is a ramp, the output is a ramp response. And we said, just as the impulse is a derivative of a step, and a step is the derivative of a ramp, the impulse response is the derivative of the step response, which itself is the derivative of the ramp response. And we can say that the other way around. We can say the ramp is the integral of a step, and a step is an integral of the impulse. So the ramp response can be found by integrating the step response, which itself can be found by integrating the impulse response. We also revisited the idea of a causal system, and we said a causal system, because it cannot anticipate an input, it means the output cannot precede the input. It cannot come before the input. So that means the impulse response cannot have a value, a non-zero value, before t equals 0. Because if your input is at t equals 0, it means your impulse response has to happen either at 0 or after 0. It can't happen before 0. If the output were to happen before 0, even though the input happens at t equals 0, then the output would be anticipating the input. It would be happening before the input, so that would be non-causal. So this is the condition for causality. We also said something really important. We said the impulse response allows us to find the output of a linear time invariant system for any arbitrary input. So even if your input isn't an impulse, so your input could be anything. It could have an input like that. And from that, I can still find the output simply by carrying out a convolution with the impulse response. Now I say simply because mathematically all it is a convolution. But if you're not inclined to carry out convolution integrals, or if the convolution integral is particularly lengthy and tedious, then today we'll look at an easier way to do this. So we will looking at how to find the output of an LTI system for an arbitrary input while knowing the impulse response without needing to carry out a convolution integral. And finally, at the end of the lecture, we said that cascaded systems can be implemented in any order. So it doesn't matter which order your systems are. So a system where the output of one, or an arrangement of systems where the output of one system is the input to the other system, that's called a cascaded system. And it doesn't matter if you put systems one way around or the other way, because you will always have H1 and H2. In the end, they will be convolved. Okay, so that was what we did last week, and I made available a large number of pencasts with relevant examples. Okay, so the test you had last week was about lectures 6 and 7, but this was recap from lecture 8. Okay, so that was last week. This week, very short lecture. Okay, so it's a mini lecture, if you like. And we'll be looking at something called the transfer function. And in introducing the transfer function, I will introduce you to something called the Laplace transform. So basically, I'll be saying that the transfer function is the Laplace transform of the impulse response. And we'll also have a problem sheet later in the week, along with a number of pencasts. And on Monday, there will be a online interactive problem class. So your next test will be on the 14th of December. So make a note of that, okay? You have a test on the 14th of December, and that will cover lectures 8 and 9. So impulse response and Laplace transform, 2 related topics, really easy. So today we have a mini lecture, it's a half lecture, and last week's lecture was really easy, or I hope you found it easy, so you shouldn't really struggle with this next test, but make sure you're ready for it. It's on Monday the 14th of December. Okay. Recap. Impulse response. Sometimes we call it HR. We generally refer to it mathematically as h of t. So the impulse response is the output when the input is an impulse. So that's just definition. H of t is what comes out of a system when the input is a unit impulse. So whatever we get out, whatever that is, that's called our impulse response. Why is it useful? Why is it valuable? Because it allows us to find the output, or the system response, for any input. So whatever input you have, you can still find the output if you know the impulse response. So your input could look something like that. The output is simply x of t, which is that, convolved with h of t, which is your impulse response. So I say simply, it's a convolution. So if you find convolution simple, then it's simple. So that way you can find the output for a system for any input. You just need to carry out a convolution between the input and the impulse response. So that's what we learned last week. Okay, so that's your convolution. So if you happen to replace that with an impulse, this should give you your impulse response. And if you think about it, when you convolve a delta function with anything, you get your original function back again. So delta t convolved with h of t will give you h of t. If that's not obvious, if that's not clear to you, then ask yourself why and spend a few minutes actually trying to prove that. Okay, you might need to remember the sifting property. Not the shifting property, the sifting property, or the sampling property of the delta function. Now I'm going to say a few words about the idea of a transformation. Okay, so we've already looked at one transformation. We've looked at the Fourier transform. And that was helpful because it took a signal from a representation in the time domain to a representation in the frequency domain. So doing that allowed us to view the same signal in a different way. Today, we're going to look at how we can do the same thing, not to look at signals in a different way, but to look at systems in a different way. But the same idea applies, that what we do in a transformation is we take some problem in some original way of thinking, which could be looking at something in the time domain, and we move it into a different domain, a different way of thinking. It could be the frequency domain. Actually moving from time to frequency, that is our transform. Going back from frequency to time, that is your inverse transform. So remember, we had the Fourier transform and the inverse Fourier transform. The Fourier transform would take you from time to frequency. The inverse Fourier transform would take you from frequency back to time. So that allows us to start with a problem and end with a solution, both in the same way of thinking, in the same domain, in the same world, in the same representation. So if we start with t, we end with t. What happened here was undone here. Why do we do that? Simply because it's sometimes easier to find a solution in an alternate format or an alternate domain or an alternate way of thinking. Just like, for example, if we wanted to carry out a convolution in time, we might find it easier to carry out a multiplication in frequency. So rather than try to solve the problem in the time domain, we could take it to the frequency domain, carry out a multiplication, which is easy, and then use an inverse Fourier transform back to the time domain. And we looked at that extensively in week 6 with the properties of the Fourier transform. So for example, so this is really just mirroring what I just said, that we could have a time domain problem that's solved in the time domain by taking it into the frequency domain, and we'd have a Fourier transform and an inverse Fourier transform. Well, today we're going to mirror that using something called the Laplace transform. And instead of having something referring to it as frequency, we'll refer to the alternate domain as the S domain. So it's complex frequency, but it's enough for us to call it the S domain. Okay, so we'll be introducing something called the Laplace transform and the inverse Laplace transform. It's much easier than the Fourier transform, especially after you've learnt the Fourier transform. That's really helpful in solving a particular kind of problem, such as differential equations. So linear differential equations are possible to solve in the time domain, but they're notoriously difficult. So finding a solution in the time domain is notoriously difficult. Now, if you've ever tried to do this as part of your maths, you will have found out how challenging it is. It's possible, it's just a large number of steps. By taking our problem from the time domain into the complex frequency domain, into the S domain, so here it's a function of t, here it's a function of s. Finding the solution is much, much easier because differentiation in time is simply multiplication by s, or s squared, in S domain. So we use simple algebra as opposed to complex algebra to find effectively the same solution. But here your solution would still be as a function of s. So to get it back in the time domain, if that's what you want, you would need an inverse Laplace transform. So you need to transform and then an inverse transform. So now for the actual detail, what do we mean by the inverse, the Laplace transform and the inverse Laplace transform? So just like we used a capital F, curly brackets, for the Fourier transform, this time we'll be using a curly L for the Laplace transform. So we have some function in the time domain, f of t, and we're going to find the Laplace transform, so that will give you uppercase f of s, okay? S is our new variable, uppercase to represent the transformed version of the lowercase f. Okay, so there's your f of s. So you integrate your function f of t, e to the minus st. Now here we are looking at Laplace transforms for causal signals and causal systems. And that will explain why we're not integrating from minus infinity. We're only integrating from 0, because we're talking about systems which are causal. So they only respond from t equals 0. So therefore, it doesn't matter if the signal has a negative component, or it doesn't matter if the signal exists in negative time. We will treat them as causal signals. Now, the inverse Laplace transform is not as easy to calculate, but the good news is we're never going to be using the inverse Laplace transform table. Inverse Laplace transform will always use tables for that. Okay, so we can use lookup tables to do both Laplace and inverse Laplace transform. But even if you calculate this integral yourself, which is generally easy, you won't need to do the same for the inverse Laplace transform. So this is what a table of Laplace transforms might look like. You'd have two columns. You'll have your time domain signal and your transformed signal. So just to fit it on the slide, I've put these two sections together. So you'd look up your signal in the time domain and find the corresponding S domain representation, or the opposite. If you need an inverse Laplace transform, you look for your signal there and you read across. Okay, these will be provided in the exam, at the back of your exam paper, and in your problem sheets. So there'll be different versions of this table, but it's basically the same information. So, back to our discussion about impulse response. So, h of t, that was our impulse response, and you were probably expecting me to talk about what would happen after we take the Laplace transform of h of t. So you'd end up with an uppercase h, and instead of t, our new variable is s. So h of t, h of s, these form a pair, not a Fourier pair, but a Laplace pair. So the transfer function is the Laplace transform of the impulse response. All right, so lowercase h of t, that's called the impulse response. Uppercase h of s, that's called the transfer function. They are the same in that they describe the same system. The difference is that this describes it in the time domain and this describes it in the complex frequency domain. H of t is the output in the time domain if the input is a unit impulse, and h of s is the input in the s domain if the input is a unit impulse in the time domain. So it's exactly the same. We're talking about the same system here. It's just different language. We can either use this or this depending on what we're trying to do. So if the input is in the time domain and you want the output in the time domain, then you might be interested in the impulse response. But if the input is in the S domain, you want the output in the S domain, you would look at something called the transfer function. And this is where it becomes interesting. Finding y of t involves convolving x of t and h of t. So that's your convolution. That's what we're trying to avoid doing. Now your output y of s, on the other hand, is x of s times h of s. So notice that convolution and that multiplication. Convolution in time is equivalent to multiplication in S. Now, we're not going through all the properties of the Laplace transform. We're not going to explain that in detail, but it's enough to know that one of the properties of the Laplace transform is that convolution in time is equivalent to multiplication in frequency, and that is often a much easier operation to carry out than that. So here we have it. If the output is the input times the transfer function, you can now redefine the transfer function simply by rearranging that and say, well, the transfer function is simply the ratio of the output to the input. So if you have some system with an input x of s and an output y of s, then we can define h of s as y of s divided by x of s. So it's the output divided by the input. But very important is this only happens in the s domain. You can only divide in the s domain because you could only multiply in the s domain. You can't do the same in the time domain. You can't say, oh, h of t equals y of t divided by x of t. You can't do that. That because convolution isn't multiplication. So this is actually really helpful. Being able to do this is really helpful. And you'll see how when we answer questions in the problem sheet. So, how do we actually find the output? So we said we can multiply the transfer function by the input, and it doesn't matter which way around you do it. You could say x of s times h of s, or the other way around. Either way is okay. As I said, you can't simply do the multiplication in the time domain. You would need to carry out a convolution. And while it doesn't matter which way round you put x and h, this is still a convolution. So really that's all I wanted to say for this lecture. I simply wanted to introduce this idea of a Laplace transform. And while looking at the problem sheet, we'll look at some of the properties of the Laplace transform. I wanted to introduce the idea of a transfer function as being the Laplace transform of the impulse response. Okay, so h of t and h of s are a Laplace pair. So that means that we can define h of s as the output of a system divided by the input, or we can write the output as the product of the input times the transfer function. We'll look at this in a little bit more detail in the Kahoot class and in the problem sheet. There are also going to be a number of pencasts available. So that's all for lecture 9. What remains is lecture 10 and 11, where we'll be looking at the same two ideas that we looked at here, but we'll look at them here for discrete time systems. So these two lectures, lectures 8 and 9, these were for continuous time systems. Continuous time systems. These last two lectures will be for discrete time systems. And hopefully you'll find these last two lectures even easier than the two lectures that you've just had. So again, finally, just to remind you, we are right now here. So we've just finished lecture 9. On the 14th of December is your next test. Last two lectures, lectures 11 and 12, will be in January. Okay, so I'll record these for you and make them available before then, but the actual problem class and tests will be after Christmas. Okay, so I hope you found that helpful. I'll see you in the problem classes that are coming up soon on Monday, Thursday and Friday, and until then, just stay safe.